In this session, let us see ideal transformer as magnetically coupled network. Okay. Before starting the concepts, first of all, we have to understand the difference between transformer in machine and ideal transformer or transformer here. Okay. The differences you will understand automatically if we go through the questions. Now, see this question. Okay. In our machine transformer, we never find such things. Okay, what does it mean? Here we are going to play with network because networks is meant for mathematical. Okay, so everything is going to be mathematics only. Mathematically, if I connect here to here, what will happen is going to be network theory. And in machine, we have fixed boundaries. Okay, our machine transformer is supposed to handle bulk of power, kVA, MVA, worth of crores of rupees. Okay, but here network theory, for example, in machines we say that power handling capacity, current carrying capacity of the conductor. Okay, so such things won't be there here. Okay, so here it is meant for kids, like kids can play. It's like toy. Okay, and if you think of machine is not supposed to play with. Okay, machine is really big thing. Okay, machine cannot be used for maximum power transfer theorem. You are not supposed to apply. Okay, or kind of impedance matching we don't do in machine transformer, but here we can use that because it is meant for mathematics. Okay, now if you see, for example, this question, we will never see such kind of question in ideal transformer of machine, but in network it is allowed. Okay, so for the network, how to write equations and how to get the answers, that's it. Okay, so that particular, for example, if I think of this as a machine transformer, first of all, we will see what is the capacity of this, what is the power handling capacity of this. Okay, so basically in machines some boundaries will be there. Inside the boundaries only we are supposed to play, but in network it's your wish. Anywhere anything can be connected and you can find out what is a response should be or solution. Okay, so if you think of here, in our machine again such a kind of play will not be there. Okay, so cascading transformer and from here to here, okay, it will not be there. If you see here, network theory, if you see here, see they have given current source. Have we any time analyzed in machine kind of transformer, have we analyzed with current source? No. Okay, ideally ours is voltage source only, and that too with a sinusoidal voltage source only, but here they have given current source. Okay, and that too triangular waveform means that it is meant for network theory. Okay, so mathematically we should be able to find the answer, that's it. Okay, now of course in this question only means one of the popular publication has given wrong answer, we will see that. Okay, next thing is, for example, take here. Okay, see, if I think of this as machine transformer, then definitely I will ask, okay, load, normally our, what is the load, means lagging or leading loads we are going to have predominantly we are going to have lagging loads. Okay, why? Most of the loads are induction motor loads. Okay, so inductive dominated loads, where you are going to have capacitive dominated loads, normally no. Okay, so I don't accept this as a load. Okay, of course reactive power compensation and all we are going to see by connecting capacitors and all, but as a load we are not supposed to accept this because capacitive dominated load will not be there, and that too they ask the output voltage across the capacitance because it is networks. Okay, so conclusion is very simple. Networks transformer means you can play, means connect anywhere to anywhere and apply KCL or KVL or mesh or nodal analysis, and let us try to find out the solution that it will be only there, means that transformer in network theory means we can play with, it's kind of toy, Our machine transformer is meant for legends. Okay, means you are not supposed to play. In machines transformer, frequency is going to 50 Hz only. It is supposed to work with power handling capacity only. It is supposed to transform power only. Okay, such things will be there in ideal transformer of machines. Anyway, coming to the point here, let us try to analyze. Okay, see here, what is meant by ideal transformer? Okay, so we say that coefficient of coupling K is going to be 1. What does it mean? Coefficient of coupling in the sense there will be no leakage. Okay, meaning that if I have some flux here, in the sense if I inject some current here, I1, okay, so some flux will be generated. That flux, basically magnetic field is a curly field, so it will form closed paths. Okay, I'm saying that this particular flux, whatever is created by this, complete flux without any leakage will travel through this. So there will be nothing kind of this flux. Okay, so there will be nothing kind of this flux. Okay, so complete flux is going to travel through the complete core, we say. Okay, if I have maybe one turn here, if I have one more turn here, okay, basically what is the logic here? Logic is very simple. Whatever the flux produced by first coil means complete flux has to go through this. What is the induced voltage per turn? N d pi by dt. Number of turn is going to be 1. So induced voltage is directly proportional d pi by dt only. Whatever may be the flux variation which is happening here, complete flux will come to here also. So flux variation occurring here is going to be same as flux variation occurring here. So induced voltage here, if I think of E across one turn, same voltage has to be induced here also, because flux is not leaking anywhere. 100% of the flux is linking here. That is one special case of magnetically coupled network. We call it as ideal transformer. Okay, meaning that if I have 1, 2, 3, 4 turns. Okay, so if I have 4 turns, how much will be induced voltage? See here, same flux is linking, same flux here, E, same flux here, E, same flux here is going to be 4E. About positive, negative and all, that will be decided by the sense of the winding or dot convention, already we know. Okay, ultimately what is the conclusion here? The moment you don't have any leakage, meaning that induced voltage per turn in one turn will be same to the all connected coils. That is the first property of ideal transformer, meaning that induced voltage, maybe let me write here, voltage per turn is going to be same. Now here we can connect voltage source, we can connect current source, we can connect two sources on two sides. Okay, anywhere, any time we can analyze, because networks is meant for play. Okay, so see here, if I connect a voltage source here, okay, so if I connect a voltage source here, let us see what will happen. Okay, so let me think of black. Okay, so supply voltage is V1, means immediately after this I am going to connect with current source also. Okay, so supply voltage is V, so how much voltage will be there here is going to be V1, same V1. Okay, now means flux is going to produce like this, is going to pi 1, okay, produced by first coil, complete flux is going to link here also. That is going to be the property of ideal transformer, there is no leakage. Okay, so point here is induced voltage per turn here, is going to be same. What is induced voltage per turn here? V1 by N1 in one turn, because N1 turns are there, equal to V2 by N2. If I have induced voltage of V2 here. Okay, so total induced voltage is V2 by N2 in one turn, equal to total induced voltage V1 by N1 voltage per turn. Okay, now let us see the dot convention. Okay, so if you see the dot convention, means, for example, if I think of my current is flowing in this direction, because from positive current has to come out, because it's a source. So if current is entering here by right hand thumb rule, flux is in upward direction. Okay, so let me keep dot here. Now, how current has to be injected in this? Actually, from starting I have been telling the same way, in which terminal current has to be injected such that this flux will aid to this flux is the dot. Okay, so if I think of, see here, right hand thumb rule, if I think of my current is entering here, it is opposing. Okay, so pi 1, this particular current will oppose pi 1. Okay, this particular current created flux will oppose that. If I think of my current is entering here, so current is entering here, right hand thumb rule, so flux will be in this direction. So if my current is entering here, automatically pi 2 will aid pi 1. So we have to keep the dot here. Okay, and by dot convention, till now whatever we discussed, so many times we discussed actually. Okay, so if I say at one instant if this dot is plus, at the same instant this dot is going to plus, so induced voltage polarities are going to be like that. Okay, now let me, this is at no load condition. In the sense, nothing is connected to the secondary, nothing is connected to the second coil. Now let us think of, if I connect something to the second coil, what will happen? Okay, see, again same story here, diagram is same. Okay, when this is positive, negative V1, positive, negative V1. Whenever this is positive, this is going to positive, negative V2. And V1 by N1 equal to V2 by N2. Okay, now if I connect one resistance, for example, if I have one resistance here, okay, so that resistance, now see here, if I have one resistance here R, okay, now if I supply some voltage here, plus minus, then always current should enter into positive terminal of the voltage. So this is going to be current I. Okay, now if I connect these two, then what will happen? Current compulsorily has to travel like this only, because plus is here, so current has to enter plus terminal of voltage if I think of resistance. Okay, so logically speaking, on one side of the coil if I connect the source, and another side of the coil if I connect any passive element, if current is entering into the dot, see here, if current is entering into the dot, okay, so current has to leave from the dot if I connect passive element here. Okay, because my passive element has to absorb power and it is supposed to deliver power. So conclusion is very simple. What is that? If my current is entering into the dot from source side, my current has to leave from the dot. Of course, in solving the problems, normally we will try to take one current entering into the dot and another current leaving from the dot. Maybe if they ask you current flowing in this direction, if they ask you in the problem how much is I2 in this direction, under that condition negative term will come. If I1 is positive, I2 is going to be negative if I consider in this direction. Okay, or if I1 is positive, I2 is also going to be positive. If I1 is positive, I2 is also going to be positive if you consider current entering into the dot and current leaving from the dot. Getting my point, right? Now see here, transformer. Is it a passive element or active element? Transformer is passive. Okay, so if I don't have this source, it cannot deliver any power by its own. It's a passive. Getting my point, right? So if I think of this as passive, okay, it is delivering some power here. If it is delivering some power here, so source has to deliver that power. Okay, so my load is absorbing some power because here voltage is there. Okay, voltage is there and some current is flowing through the resistance, so some power is being absorbed here. And my transformer as a whole is passive, so transformer cannot deliver any power. So whatever the power is absorbed at the load side, compulsorily the same power should be delivered by the source side. Okay, now means power absorbed here should be equal to power delivered here or not? Yes. Okay, so see here, what is the power absorbed here? Okay, already voltage across resistance I know, so that is V2 square by R is going to be power absorbed by resistance. Okay, now if I feel, for example, this is a black box. Okay, so this is a black box. From here to here is a black box. Okay, so I am sitting at the source side. Okay, so here somewhere some power is being absorbed, meaning that same power it has to deliver. Otherwise, how can it absorb power? Okay, it is absorbing power, meaning that it has to deliver that power. Okay, so how much power it is delivering? See here, this is going to be V1 and here some resistance dash. Okay, so equivalently here if it is absorbing power, the same power it is supposed to deliver. So here absorbed power equal to here delivered power or not? Yes. Okay, so see here, V2 square by R, V square by R should be equal to V1 square by R dash. Okay, so let us think of V1 square by R dash. R dash should be equal to V2 square by R. Okay, same power absorbed here should be power delivered here. Okay, so V2 square by R is the power absorbed here, and V1 square by some R dash, virtual, okay, model. Okay, now how much is R dash? R dash is going to be V1 square by V2 square. Okay, V1 square by V2 square into R. Okay, already EMF per turn, already we know it or not? Yes, EMF per turn, voltage per turn here and voltage per turn here is going to be same, already we discussed. So that equation is going to be EMF per turn equal to voltage per turn. So meaning that V1 by V2 should be equal to N1 by N2. Okay, if I apply this here, so that R dash should be equal to N1 by N2 square into R. N1 by N2 square into R. If you are transforming this resistance from here to here virtually, if you feel, means this is going to be complete black box and my source is delivering some power, meaning that I can completely model this on one side as R dash. Okay, so what is the conclusion here is going to be N1 by N2 square. Now, from current point of view, let us see. From current point of view, see here, from here to here, for example, if N1 is more, N2 is less. Okay, I hate the concept of turns ratio. Okay, because I am from electrical, I know. Okay, turns ratio should not be used. It means already we discussed that in transformer machines. Okay, if N1 is more, N2 is less. Okay, under that condition, N1 is more, number of turns are more, voltage per turn is same, meaning that V1 should be more. N2 is less compared to N1, N2 is less, number of turns are less, so voltage per turn is same, so number of turns is less, so voltage will be less. Okay, so from low voltage side, actually this can be called as low voltage side, this can be called as high voltage side. Low voltage side to high voltage side, if you move, what is happening? My resistance is going to be increased because N1 is more, N2 is going to be less. Okay, so from low voltage side to high voltage side, if you move, resistance magnitude is going to be increased by square times. Just remember that way, it's enough. Okay, now here power absorbed and here power absorbed should be same or not? Yes. So from here to here voltage is reduced. Okay, so here N1 is more, N2 is less. So from here to here voltage is reduced, meaning that current magnitude should be increased for the same power. So I2 should be increased, I1 should be less. Getting my point, right? So I can say that all over, I can conclude that. Of course, from this also I can conclude, but it's not required. So V1 by V2 equal to N1 by N2. Okay, V1 by N1 is the voltage per turn in first coil. V2 by N2 is going to be voltage per turn in the second coil, should be same. Okay, and also if you think of V1 is more, I2 should be less. I2 is more, sorry, V2 is less, I1 should be less. Okay, in other words, see here, V1 into I1 is the input power, V2 into I2 is the output power. Okay, so from this way we can conclude rather than discussing in depth and all, because we electrical engineers anyway in transformer we analyzed in depth. Okay, so input power is V1 I1, output power is V2 I2, output power equal to input power. Okay, we can close this deal this way. Now let us think of inductance L, directly proportional number of turns square. Okay, so directly we can consider directly proportional number of turns square. If you want derivation and all, already we have in transformers, we analyze detail. Okay, number of turns square. So L1 directly proportional number of turns square, L2 directly proportional number of turns square. Okay, so L1 by L2 equal to N1 by N2 square. Okay, now if I think of mutual inductance, what is mutual inductance? Is going to be K into under root of L1 L2. Okay, so K is going to be proportionality constant of 1 by my tight coupling. Okay, total flux of primary or first coil is linking with the second coil, so this is going to be 1. So L1 is directly proportional to N1 square, L2 is directly proportional to N2 square, under root is going to be N1 N2. So I can say that L1 L2 M equal to L1 directly proportional to N1 square, N2 square, N1 N2. Okay, so in this way these are going to be conclusions taken. Okay, so with these conclusions we can solve the problems. Once we solve some problems, then we'll come back to T model also. Okay, let us think of if I connect current source. Okay, so then you see here, if I connect a current source, just a minute, if I connect a current source, see the difference, because you should know the difference. Okay, so if I connect a current source of, just a minute, of I1 is the current source flowing through N1, will create flux pi 1. Okay, so this particular flux will induce voltages here. Already dot convention we know, we need not bother about it. Here induced voltage of V1. Again, whatever may be the flux here, total flux is going to link here. So voltage induced per turn here should be equal to voltage induced per turn here. So V1 by V2 should be equal to N1 by N2. Problem solved. Okay, now if I try to connect a resistance here, what will happen? Okay, so if I try to connect a resistance here, then what will happen? Means the moment positive is here of V2, so current should enter here, I2 will go like this. Okay, so if I2 is going like this, okay, basically one current is entering into the dot, another current is leaving from the dot. So if you try to do how pi 2 will be, because after this discussion only we will go back to when voltage source is connected, then you will get a bit clarity. Okay, so means see here, my current is leaving from the dot, it is absorbing power, so it has to deliver power. So if I think of plus minus V1, so V1 into I1, my current is coming out of positive terminal, so it will deliver power, it will absorb power, that's it. Okay, anyway, let us think of the direction of pi 2. See here, my pi 1 is in this direction, right hand thumb rule, my current is entering, right hand thumb rule already we know. Okay, my current is leaving from here, so if you see, it is leaving from here and it is entering into here, so it is entering into here, my pi 2 is going to be opposing. Okay, so the moment pi 2 oppose, as I said in one of the popular publication, they have done this mistake only. Okay, so the moment pi 2 occur, what is the net flux here? Net flux is going to reduce, or at least I can say net flux is going to vary. Okay, if net flux vary, here voltage and here voltage are going to vary. It's okay. Why? Because for a current source, current is known, but voltage is unknown. Any voltage it can be. Okay, so is this a current source or not? Yes, for a current source, if voltage, for example, if I think of this flux magnitude is reduced, so d pi by dt is going to be reduced. Under that condition, this particular voltage is going to reduce. It's okay, because for a current source, current should be as specified, not voltage. So here the moment you connect current source, voltage is going to be reduced the moment you connect the load, or flux is going to be reduced. Okay, now if I think of voltage source, okay, so if I think of voltage source, see it here. Okay, if I think of voltage source, basically whoever has gone through our ideal transformer, okay, so automatically they will understand. Okay, see here, my current is going like this. Okay, so my first flux, if you see blue, okay, so my current is entering here, right hand thumb rule, my operating flux is going to be pi 1. Okay, one logic here, n d pi by dt, n d pi 1 by dt is the voltage here or not? Okay, induced voltage directly proportional to n or equal to n d pi by dt. Number of turns are going to be constant and voltage is going to be constant, because this is ideal voltage source. So ideal voltage source can give any amount of current, but voltage should be constant or as specified. If I think of this as a sinusoidal voltage source, it should be sinusoidal voltage source only, and sinusoidal voltage only should be induced here. Now what about the current value? It can take any amount of current. Okay, so it can take any amount of current and it can supply any amount of current, because for a voltage source, voltage is known, current is unknown. Any amount of current can be taken depending upon the load. For a 10 volts voltage source, if I connect 1 ohm resistance, how much will be the current? 10 volts divided by 1, 10 amperes. For a 10 volts voltage source, if I connect 10 ohms resistance, 10 by 10 is going to be 1 ampere current. So through voltage source, current can be of any value, but voltage should be as specified. So the moment voltage is constant, number of turns are constant, d pi by dt also should be constant or not? Yes. So at no load condition, in the sense once this is not there, once this is not there, this is not connected, under that condition pi 1 will come. Okay. Now for example, red. Now see here pi 2, if you see, current is coming out of the dot, current is coming out of the dot, so pi 2 will come like this or not? Okay. So same, whatever the way we have done. Okay, current is coming out here, current is entering here, current is entering here, pi 2 should be in upward direction. So if pi 2 is in upward direction, net flux is going to be pi 1 minus pi 2. Okay, so this net flux, will it change? No. Why? If net flux changes, net voltages has to be changed. If net voltage changes, but it is connected with ideal voltage source, voltage should be same. Getting my point, right? So logic is very simple here. What is that? When voltage source is connected, means my induced voltage here or voltage should be same, meaning that flux should be same. So this extra pi 2, it will be killed. It will be killed by taking extra current. That way I1 will come. Getting my point, right? So for a voltage source, for example, if it is not there, current will be 0. Okay, in the model, in the T model, I'll tell you when current will be 0 and when current, current magnitude, kind of no load current in transformer increase and all, I will tell you in T model immediately after this, once problems are solved. Okay, so see here, if I2 is 0, how much is output power? V2, I2 should be 0, I2 is 0, total output power is 0, so total input power should be 0. Okay, so V1 will be there, current will not be there. Okay, ideal transformer, I will tell in T model about this. Okay, so if this current is there, this pi 2 will come. But net flux should not be changed because it's a voltage source. So this particular flux will be killed by taking extra current. Again operating flux should be pi 1 only. Okay. So the moment voltage source is connected, operating flux is going to be constant. But current will vary depending upon the load connected here, depending upon the passive element magnitude connected here. This current will vary. But voltage is constant. But if you think of when current source is connected, current is going to be constant. Because for a current source, constant in the sense, of course, time varying constant, I can say. So if I connect current source, okay, under that condition, current source magnitude is going to be as specified. But what about the voltage across this can vary? So the moment voltage across this can vary, operating flux can vary. So if I connect this load here, net flux is going to reduce. If net flux reduce, or at least we can say vary, okay, automatically voltages will vary. So if I open circuit this, voltage magnitude here, if I close this, voltage magnitude here differ. Okay, so in one of the gate problem, that's what I said. Okay, so one of the guys has given a wrong answer here. Okay, see here current source is there, no? Okay, so the moment it's a current source, current is as specified, but what about the voltage can vary. So if switch is open, under that condition current will not flow here. Under that condition complete I1 will give you some flux. Okay, now the moment I close this switch, I2 will flow. Because of that pi 2, second coil flux will come. So pi 1 and pi 2, net flux is going to vary. So net voltage is going to vary. Okay, so in this problem, if switch is open, voltage, when switch is closed, voltage across this differ. Now see here just once. Okay, so see here, when current source is connected, if this particular resistance is not there, this I1 will produce pi 1. Okay, but for example, if I connect this resistance, then current will go. Okay, so when current is entering into the dot, current has to leave from the dot, because here it's a passive element, it is supposed to absorb power. When power is getting absorbed, current will come out of the dot. Okay, when current is coming out of the dot, pi 2 will come. Okay, net flux is going to vary, net voltage is going to vary because current is constant here. But if you think of here, see, if you think of here, voltage is constant, kind of given voltage, I can say. Constant means, of course, time variance should be there, otherwise voltage will not be in use, no, n d pi by dt. Okay, so here voltage is constant, kind of given. Okay, so the moment voltage is given, current can be any value, voltage should be as given. So as this voltage is given constant, kind of constant, time varying constant, so V1 should be constant, any amount of current it can take. So the moment induced voltage should be constant, meaning that operating flux d pi by dt should be constant. So if something is coming from here, if something is coming to disturb pi 1, it will take some more component of current to kill it. Okay, now about this more in-depth analysis you can observe in our ideal transformer or transformer in machine. Okay, now we will solve problems.